Hello friends. So, we saw in our previous lecture how the domain integrals that arise in the approximate solution of equations of motion in two dimensional continuum arise, and how they are solved, and how those integrals involving various powers of x in triangular geometry they are evaluated. Now, so after taking care of the domain integral, there is still one boundary integral term that is left, that is still to be evaluated. So, how do we evaluate the boundary integral in the triangular geometry? So, triangular geometry, the boundary will of course be straight line, and it is to be evaluated at along the closed path. So, this is the boundary integral that is to be evaluated in the closed path. So, I go from I and j. So, that is, and from j to k and from k to I, and that is the normal outward normal positive direction, and the outward flux is of course going positive outward normal. So, there are two elements, element E and element E plus 1. So, boundary integral in the weak form of the weighted residual statement, they require integral along the closed path, and for simply connected domains like finite elements which are which do not have any gaps or in any hole within the interior of the element. So, it only refers to going along the edges of the element in the counterclockwise order. So, the normal, the direction, positive direction is considered to be the normal, outward normal along the on the edge. So, that is the important thing to note, that is positive direction, what is the direction of the normal. So, how do we evaluate these coefficients, these boundary integrals? So, the boundary integrals that you look at like this. So, this is the boundary integral. So, gamma is the integral of the element that we have, right. So, how do we evaluate these boundary integrals? Now, first thing is we need to appreciate that in the interior, if I have let us say element, if I have some domain which are modeled using finite elements. So, and there are some tractions here on the edge of the element, and this particular is defined by this element, and there is another element like this. And so on. So, the entire domain is discretized using this kind of 3 noded triangles. So, this is omega e, and let us say this is omega e plus 1. So, omega e, the boundary integral would involve this edge and this edge. Omega e plus 1 boundary integral would involve this edge and this edge. So, let us look at the boundary between, common boundary between omega e and omega e plus 1, and that is what is seen here, omega e and omega e plus 1. So, the boundary integral positive direction, they are all outward positive. Now, when a boundary is shared between two adjacent elements, then this outward normal would fluxes would cancel each other out, right. So, this is same thing as what we had in the case of first one dimensional element, the common nodes between two elements, when they add together. So, secondary variables, they tend to cancel out each other because of their opposite signs, and this is the same thing. So, secondary variables on two different elements, adjacent elements on the common boundary, they turn out to be of opposite signs and they would cancel out, and therefore, it does not really require I mean we do not really need to evaluate these boundary integrals when the boundary is in the interior of the domain. For example, this boundary, this is in the interior of the domain, the problem domain is this, right. So, we need to evaluate this boundary term only when the element boundary coincides with the problem boundary. Any boundary of the element in the interior of the domain, we do not really need to evaluate this boundary term, because those contributions would be cancelled by corresponding contributions from the adjacent elements. So, we do not really need to evaluate these boundary terms, interior boundary terms, and only the boundary term has to be evaluated when it is coinciding with the element boundary. So, the boundary integrals are evaluated to be are only required to be evaluated only and that on that part of the element boundary that coincides with the boundary of the original domain. So, element boundary is the same as the part of the original domain boundary. Of course, one element cannot cover the entire domain boundary. So, one element boundary can have only part of the original domain boundary. So, for the element boundaries in the interior of the domain, these contributions to equivalent nodal forces get cancelled with the contributions coming in from the neighboring elements. So, the secondary variables are of the opposite signs and they would cancel out along the inter element boundaries. So, effectively it is like saying some value minus some value is an approximately equal to 0, because 0 cannot be exactly computed on digital computers. So, why approximate 0 by something nearly 0 when we know that in practice it should be 0. So, now we focus only on the edge tractions, only on the boundary which coincides with the domain boundary, original problem boundary. So, it 3 noded triangle and this particular let us say ijth edge, ij edge coincides with the boundary of the element, boundary of the problem. So, this is where we need to calculate the secondary variables and they will be evaluated for, there are 2 nodes I and j. So, they will be evaluated as the forces that are going to equivalent nodal loads on the element on the node I and j. So, how are they going to be there? So, there can be 2 possibilities. I mean they are any kind of tractions can be resolved into 2 orthogonal direction, normal and tangential. So, sigma n is the normal stress on this edge and tau is the shear along this edge I j, right. So, when we do that, then multiplied by this is what naturally comes out during that evaluation. So, sigma n n x minus tau n y multiplied by the weighting function, that will be same as the shape function and that has to be evaluated along this boundary. So, this is of course q x along the, if I resolve along x and y direction. So, these are the tractions that we have. So, the entire boundary gamma substituted we can break it down into 3 parts. So, 0 to h I j. So, along the I j edge, along the j k edge, along the k j k I edge. So, I now go through each of these once in a one at a time. So, from I to j, so that is the length h I j, right. So, the integral becomes we are only looking at this particular part of the boundary. So, this boundary is defined by some variable, local variable starting from 0 and going to h I j at this point. Similarly, j k, it goes from 0 and comes to k at a value of h j k. So, we can define, the idea is it is easier, instead of working with x y, it is easier to define local frame of reference such that one particular axis coincides with the edge of the triangle that we are looking at. So, we define S t frame of reference and map it to global x y frame of reference, such that S variable, one of the local coordinate variable, varies from 0 to length of the edge, and that is what we are doing here. So, d s is the S is the variable that we are looking at, local variable. So, the element boundary I j is defined as S varying from 0 to h I j. Element boundary j k is defined by S variable going from 0 to h j k, and element boundary k I is defined by S variable going from 0 to h k I. And similarly for tractions, I mean the in y direction. So, you can convert it I mean along x and y. So, normal and tangential can be converted to global x and y. So, this is normal and this is tangential, they can be oriented along x and along y using the direction cosines. So, just take the projection along x and y, and that is the basic components. So, after in order to do that, once we have this, then we can evaluate this integral very easily. If we know, if we can somehow convert this also into function of s, right, and that we will do by defining the linear mapping. So, evaluation of these integrals is simplified if we consider a transformation of variables in x y coordinate system to a new coordinate system S t with the origin at node I mean at one at a time. So, for each edge we take it one at a time. So, for edge I j we consider the origin at node I. So, these two coordinate system, it is a linear transformation. So, I define x is equal to a 0 plus a 1 s plus a 2 t, y is equal to b 0 plus b 1 s plus b 2 t. This is the general linear transformation that we can have, as general as it can get, nothing more to be added. So, we have not missed out anything, lower order terms, and so lower order term would actually capture the constant shift of origin, and linear terms of course define the linear mapping. So, once we substitute the values of x and y for nodes I and j and k, and we get the complete mapping between these three x 0, a 0, a 1, a 2. So, there are three coefficients. So, I define x I as 1 0 0. So, S is 0 at node I and t is also 0. So, that is the origin, and then x j again t is 0 along that line I j, but S value is equal to the length of the element, and k we need to define what is the value of node k along with respect to S t coordinate direction, right, with using S t coordinates, local coordinates S t. And once we have this mapping, then a 0, a 1, a 2 can be directly computed by taking the inverse or even the forward substitution. It is a lower triangular matrix. So, it can be solved easily, even the inverse is not required. Similarly, b 0, b 1, b 2 for coordinate y, and a direct solution for a and b can be computed by using forward substitution and by solving this triangular system of equations. And since side I j is defined by t is equal to 0 in the S t coordinate system, it is sufficient to substitute x is equal to linear function of s and y as a linear function of s, and t is obviously 0. So, no point in adding that term, no additional benefit. So, it is a linear interpolation, as you can see, it is a linear interpolation between x y coordinates of I and j as s varies from 0 to h I j. And once we have this mapping for x and y in terms of s and t is of course is to be substituted as 0. So, they can be substituted, x and y values can be substituted in the expressions for w or weighting function or the interpolation functions as a function of x and y, and we can obtain these expressions which can be evaluated along the edge as s ranges from 0 to h I j in along the I j edge I j, right. So, these are the two interpolations. So, n I and n j they can be replaced by w I as a function of s and w j as a function of s, and these can be used for evaluating. So, the boundary term now only needs to be evaluated with respect to one variable s, and that can be integrated very easily and analytically or numerically using quadrature rules, and the equations can be solved. So, the weighting function corresponding to other node k is 0, because node k receives no contribution from the equivalent nodal forces due to edge traction, because edge tractions are only coming on the node I j. So, the other node does not really matter. So, similarly for the next element I j, for the next boundary j k, again similar exercises can be done, and local coordinate axis can be defined, and weighting function or interpolation functions x and y can be substituted with corresponding values, corresponding variations with respect to s and t, and then evaluating it at t is equal to 0, we get one dimensional variation in local coordinate s, which can be easily evaluated using a one dimensional integral. And once we understand this process, it is easy to develop just a one dimensional Lagrangian interpolation and get on with it without going through the complete intermediate details of calculation. And with that, we can compute the complete domain integrals and boundary integrals, and we can work out our element level equilibrium equations for one element, then we go to the next element, and so on until, and then we can start assembling the equations, element level equilibrium equations, impose natural boundary conditions at the element level equilibrium equations, and then assemble in the global equations, and then impose the essential boundary conditions on the primary variable, and then solve the system of equations. That is the complete finite element solution. So, this is all for triangular family. We will now, in our next lecture, we will start with another domain that will be, instead of triangle, I can as well have a rectangle domain which can be used. So, obviously for rectangle I need 4 nodes, at least 4 nodes, but one extra node and variable, but the advantage is I can it is possible to cover larger portion, larger domain with fewer elements. So, that is more economical, but there are other I mean we cannot have all according to our wishes. There is a penalty to be paid for that, and that we will see in the form of additional terms coming from the higher order polynomial approximation, which do not contribute to the convergence or rate of convergence of the approximate solution, but that is a necessary fallout of having larger number of nodes than what is required by the complete polynomial of a certain degree. So, we will continue with our discussion on rectangular family in our lecture next lecture, and after that we will try to explore the use of these elements in solving a real sample example problem that will kind of put everything, all pieces of the jigsaw puzzle in one whole picture. Thank you.